15 billion units. Exactly this many LED light bulbs are produced every year. Why does an item costing a few dollars drive an industry worth over 100 billion US dollars? The unit cost seems low. However, the volume illuminates nearly every corner of the planet. But this is just the beginning. Production starts with a semiconductor chip smaller than a speck of dust. One can notice assembly stages measured down to the micrometer. Gold wire bonding connects the core. It is thinner than a human hair, yet essential. At first glance, the chip looks ready, but in reality, it requires color conversion and protective encapsulation. It gets more complex further on. Large-scale light testing verifies the output. It is visible how chips become emitters. Billions of light sources are now ready to brighten the world every day, over 100 years. Exactly the time humanity accepted a costly trade-off. Vast amounts of energy were burned just to produce a small amount of light. One can notice how Edison's incandescent bulbs glowed with intense heat, while fluorescent lamps relied on toxic mercury. The world longed for a cleaner, cooler, and more durable source. But this is just the beginning. Why did the light-emitting diode stay in the background for so long? It was simply not powerful enough. For decades, it appeared only as faint red indicator lights on control panels. Traditional lighting continued to dominate the industry completely. It seems simple to change color, but in reality, this limitation posed a defining challenge. The industry waited. If a blue diode could be created, everything would change. It gets more complex further on. In 1994, Japanese engineer Shuji Nakamura discovered a suitable semiconductor material. This compound was the key. It allowed blue light emission reliably for the first time. This breakthrough made white light possible. One can see how the distinct blue emission enabled the full spectrum to finally take shape. The technology advances to the next level from here. A single microscopic particle of dust is enough to ruin thousands of chips at once in the manufacturing area. Why does the entire facility operate as a massive, hermetically sealed clean room? It might seem excessive to mandate such strict isolation for a simple light source. But without this absolute sterility, the delicate semiconductor structure would be compromised immediately. Engineers and technicians are required to change into full protective gear, including one-piece cleanroom suits, hoods, masks, and gloves. One can notice how they pass through high-pressure air showers, designed to strip away any remaining contaminants or lint. At first glance, this preparation seems like a mere formality, but in reality, it is the only way to protect the crystalline substrates, most commonly sapphire. Anti-static footwear prevents even the slightest discharge during movement. But this is just the beginning. Because the environment is now secure, the sapphire substrates are loaded into epitaxial reaction chambers. The temperature inside rises to extremely high levels to facilitate the reaction. Gases containing gallium and nitrogen are introduced, flowing across the sapphire surface. It is visible how the elements bond atom by atom, crystallizing into ultra-thin layers far beyond the limits of human vision. The process is only gaining momentum. Specialized semiconductor layers are formed and stacked with precise order to create a critical p-n junction structure. Inside this junction, charged particles collide as soon as an electric current flows through the chip. Energy is released instantly in the form of light. This is the moment LED light is born at the atomic scale, ready for further processing. Millions of semiconductor structures lie hidden on the surface after the process of epitaxial growth. To the naked eye, the wafer appears smooth and mirror-like. Why does this polished disc remain dark and inactive? At first glance, it seems ready, but in reality, the electrons have nowhere to flow. The structures are not capable of producing light yet because they lack the necessary connections. But this is just the beginning. To transform these layers into functional LED chips, the wafer enters the process of photolithography. One can notice how the processing area is bathed in controlled yellow light to protect the chemistry. The surface is thoroughly coated with a light-sensitive material known as photoresist. Ultraviolet light is then projected through a precision mask. This light draws microscopic patterns with accuracy down to individual micrometers. Unwanted regions are washed away, leaving behind an intricate network of ultrafine circuit features. It is visible how the blueprint emerges from the flat surface. Transition to the next level. Next, the wafer is transferred into a vacuum chamber. An extremely thin layer of metal is deposited on the surface to form the electrical contacts. The equipment gradually creates the conductive pathways required to power the device. Everything only gets more complicated. At this stage, the entire wafer has effectively become a massive light circuit board. It contains tens of thousands of individual LED chips, all formed simultaneously across the disk. They are fully structured but still physically connected. The material is now waiting to be separated in the next stage of production. Tens of thousands of identical LED chips lie fully formed across the surface of the wafer, awaiting the next decisive stage of production. Beneath the mirror-smooth appearance, the material is, in fact, a microscopic map arranged in perfect geometric order. A high-energy laser system takes over the operation, utilizing an extremely precise beam focus. Guided along pre-calculated scribe lines between each sector, the laser cleanly slices the wafer into thousands of tiny square dies. One can notice how the beam moves with calculated speed to minimize residual stress that could otherwise damage the internal structures. But this is just the beginning. Each individual LED chip, once separated, measures only a few tenths of a millimeter across. Why is such extreme precision required during the cutting phase? The chip is smaller than the tip of a needle, yet it contains a complete light-emitting region and a complex semiconductor layer. At this scale, even a microscopic fracture is enough to render the fully formed PN junction non-functional. Immediately after cutting, the components pass through an automated inspection system. One can see how each chip is briefly powered on to verify that it emits the correct color and operates at the proper voltage. At first glance, this seems like a routine check, but in reality, it is the primary filter where defective chips are removed on the spot without mercy. Only those that meet all specifications are allowed to continue their journey. The process is only gaining momentum. After the wafer has been cut, the thousands of tiny LED chips remain firmly attached to a thin carrier film. In this state, robotic systems cannot pick up individual chips with micrometer-level accuracy. Therefore, the film is fed into a crystal expander machine to prepare the grid. Uniform tension is applied from all four directions, stretching the material outward. It is visible how the chips gradually separate from one another as the film expands. This increases the spacing between them according to pre-calculated dimensions. The result is a perfectly ordered chip grid, now ready to be transferred to the automated pick-and-place system for the die bonding stage. Fractions of a millisecond. This is the specific time frame in which the robotic arm completes a single cycle of operation. The pick-and-place system transitions directly to the die bonding stage, where microscopic LED chips are fixed onto a metal lead frame containing two terminals, the positive anode and the negative cathode. Why must the automated machine dispense the adhesive dot with accuracy down to individual micrometers? The primary goal is simply to anchor the chip securely in place. However, the adhesive also provides an efficient path for heat dissipation, making the exact volume and placement critical. The expanded film carrying the separated chips is then fed into the machine for processing. Industrial vision cameras scan the entire surface, automatically identifying the exact coordinates of each chip, as well as the metal pads on the lead frame. one can notice how the system calculates positional offsets within just a few micrometers. This ensures that every component is placed with extreme precision before the mechanical arm descends. At first glance, the operation appears to be a standard routine, but in reality, the robotic arm operates at near instantaneous speed to pick up, rotate, align, and place. A gentle downward force spreads the adhesive evenly, preventing the formation of air bubbles and ensuring the chip remains perfectly level. It gets more complex further on. A misalignment of just 20 to 30 micrometers can cause color shift, reduce the LED's lifespan, or even lead to immediate failure in the next processing step. Therefore, once an entire strip of chips has been placed, the lead frames transfer immediately into a thermal curing oven. A stable temperature is maintained inside for several minutes to finalize the bond. The adhesive fully cures, permanently locking each chip into position as a unified structure. The component is now ready for further processing. 99% pure gold is the material essential for the internal wiring of the unified structure. A spool of this wire, holding a diameter of 18 to 25 micrometers, feeds continuously into the automatic wire bonding machine. It is visible how the fine thread, 3 to 5 times thinner than a human hair, enters the system after the LED chip is secured to the lead frame. But this is just the beginning. One can notice how high-resolution industrial cameras scan each individual chip and its lead terminals. Why does the system calculate positions with accuracy down to just a few micrometers? The process moves at an incredibly high tempo. This precision is necessary because the machine must align coordinates exactly to ensure the circuit functions correctly. It gets more complex further on. A tiny gold ball forms at the very tip of the wire through a calibrated combination of heat and ultrasonic energy. The mechanism descends to press this ball onto the chip's electrode, establishing the first bond point. One can see the wire being drawn immediately into a carefully shaped arc before settling. The head lowers onto the metal lead to form the second bond. The wire is cut cleanly as the machine instantly targets the next chip. It does not end at this stage. At first glance, the operation seems like a chaotic blur of speed. But in reality, every step maintains uncompromising precision. Each gold wire loop is tightly controlled regarding loop height, adhesion strength, and tensile force. This guarantees reliable electrical connection and long-term stability regardless of the pace. Technicians inspect every bond under high magnification microscopes to verify quality. Any LED showing weak or imperfect bonds is removed immediately from the line. Thus, only fully qualified components proceed to the next stage of production. 1/10,000th of a gram, exactly the accuracy level of the analytical balance used to weigh raw phosphor powder. This precision is equivalent to approximately 0.0015 grains. After the gold wire bonding and initial inspection are completed, the LED frames transfer to the phosphor coating area. Engineers weigh the raw material with absolute care to ensure the mixture matches the strict requirements. But this is just the beginning. Multiple colored powders are blended together in the preparation zone. Why do engineers blend yellow, orange, and pink phosphors in calculated ratios? It would seem simpler to use a single standard pigment for coating. However, this precise combination is necessary to define the specific target color temperature of the final light source. The powders are sent to a high-speed rotary mixer to merge with liquid. Blades inside the chamber disperse the phosphor evenly throughout the epoxy solution to create a homogeneous compound. One can notice how the mixture becomes a uniform liquid before being loaded into the dispensing cylinder. Thousands of LEDs mounted on lead frames feed into the machine chamber. Ultrafine needles descend to deposit the mixture onto each individual chip. It gets more complex further on. The machine dispenses a volume accurate down to millionths of a liter, or approximately 0.00003 fluid ounces. At first glance, this looks like a simple mechanical action, but in reality, this thin coating is responsible for converting the chip's native blue light into the white or amber light visible to the human eye. Without this layer, the LED would remain monochromatic. Once coating is complete, the entire tray of LEDs is placed into a curing oven. The equipment operates at approximately 302 degrees Fahrenheit. The heat forces the epoxy to fully harden, permanently locking the phosphor layer in place. It is visible how the surface creates a uniform optical finish across all LEDs in the batch. And this is not the limit. A fascinating detail lies in the physics of the light itself. No semiconductor chip naturally emits white light. In reality, they always produce blue emissions. The yellow phosphor layer acts as the transformer that creates the white light we perceive. Once the chips and gold wires are securely fixed, the entire lead frame strip transfers into the epoxy molding area. This is the stage where the signature transparent lens takes shape. Liquid epoxy resin is injected into steel molds containing hundreds of precisely shaped cavities. These molds are designed to create standard forms, such as 5mm round heads, flat tops, or oval lenses. One can observe the viscous liquid filling every void to encapsulate the components. The filled molds then move into a circulating thermal oven operating between 248 and 302 degrees Fahrenheit. Under this carefully controlled heat, the epoxy undergoes molecular cross-linking. The substance gradually transforms from a viscous liquid into a solid, crystal-clear structure. When the curing process is complete, the LEDs are released from the mold in their final form. A rigid, transparent plastic lens now encapsulates the semiconductor chip and gold bonding wires, leaving metal leads extending cleanly from the base. The component is ready for the next phase. Hundreds of lamps appear as the steel mold opens to reveal the cured product. The epoxy has fully solidified, extending cleanly from the base on a long LED strip. One can notice the units seem finished, yet all connect on a single metal lead frame. But this is just the beginning. Why is the product still categorized as only a semi-finished component? It looks ready for use, but the units remain fused together. Before separation, operators perform a quick visual inspection of each strip to ensure there are no molding defects. At first glance, cutting the frame seems routine, but in reality, it demands mechanical precision. The strip enters a deframing machine where cutting blades and metal punching mechanisms operate with extremely high accuracy. It gets more complex further on. In just a matter of seconds, the blades sever the connections. The thin tie bars linking the LEDs are cleanly cut, releasing each package as an individual unit. They are now precisely formed to their standard dimensions, ready for the next phase. A fraction of a second is all the time required for the automated electro-optical system to fully evaluate the quality of a single diode. After the individual LED is separated from its metal frame and holds its form to standard dimensions, it enters the testing chamber. In this brief instant, the component is powered on and flashes brightly. Industrial cameras and optical sensors immediately capture the performance data, measuring brightness, color output, operating voltage, and color temperature. Why is such high-speed precision necessary for every single chip? To the naked eye, the flash of light appears instantaneous and uniform across the batch. However, the sensors identify subtle deviations invisible to humans, which is critical for the next phase. At this very stage, the binning system begins its complex operation. Based on the collected measurement data, the machine sorts each LED into distinct groups according to brightness level, color characteristics, and electrical voltage. One can notice how pneumatic mechanisms rapidly fire, directing every unit into its corresponding compartment with mechanical rhythm. At first glance, This seems like simple sorting, but in reality, it guarantees that when these LEDs are assembled on a light strip or panel, they emit perfectly uniform light without color shifts. But this is just the beginning of the final phase. From here, the qualified LEDs move on to the lead forming and wire handling stage. It is visible how metal leads are shaped, aligned, and secured onto specialized conveyor systems, preparing them for downstream assembly within the production line. LEDs that have passed all inspections move on to final packaging. To prevent corrosion or damage, they are carefully dried and sealed in moisture-resistant bags or trays. The system applies labels with specific binning data, batch codes, and production dates. The finished shipments are then secured and transported worldwide to factories producing LED strips, displays, toys, and electronic devices. The technology is now ready for final assembly and delivery to consumers. Billions of diodes prove that LED lighting has become an indispensable part of modern life. Why is the manufacturing context so critical? At first glance, the result seems simple. But in reality, familiar materials are created through precise and meticulously engineered manufacturing processes. One can notice the strict assembly, but this is just the beginning. Similar journeys of discovery continue here. It is visible how the industrial world operates down to the smallest details. Thus, the exploration moves to the next phase.